Do you find metal and states of metal challenging, or do you really enjoy doing such questions? Either way, let's try some questions today. Hi, I'm Mr. Long and I'm a science teacher today. Now, if you have not tried this before, do pause the video at the start of each explanation to try doing it. If you have done it and you're watching this for corrections, well, get a green pen ready, underline what you need to underline, write down the annotations that are also written on the worksheet, and of course, write down the answer at the end. If you don't understand, always just replay the video again and watch it again. Let's get started. Alice placed a deflated balloon and another similar inflated balloon on a balance. Deflated means the air has escaped from the balloon, and inflated means air is filling up the whole balloon here. Now, this is a balance. A balance is used to compare masses of two objects. Right, is to compare the masses. So these are the two objects. And if it tilts down this way, if it tilts downward on this side, it means that this object here, this object that is in red, has a larger mass. It has a larger mass or greater mass. Now, never say heavier mass. Alright, never say that, because mass is the amount of substance in an object, in a material. It is not the weight. That is about forces, which you will learn soon in P6 term 2. So what property of air does the above activity show? Since this balance is used to compare masses of objects, therefore the activity shows that air has mass. Now, there's nothing about shape or volume or compress. If it's about volume, there should be something about cubic centimeter or milliliter or liters. These are all units that we use commonly to measure volume. It's not about shape. Shape, you will find different kind of containers. Alright, if it's about shape, there's nothing about this in this question. It is not about compressing. If you're compressing air, very often you will see a syringe, alright, with a plunger, and that's when we talk about air is being compressed or not. This one, clearly, because of this apparatus called a balance, it is about comparing mass. Therefore, the answer is air has mass. Next question. Now, of course, clearly, you will see some balance here. And remember, a balance is used to compare masses. Now, instead of two objects, there are three objects here. Notice A and B here. It tilts down this way. So that tells you A has a greater mass than B. So I can do a working like this here. I can put down here more and least. I think it's better to put down most mass, the least mass. So on a scale like this, where would A and B be? A definitely will have more mass than B. I'll put A above B. Now comparing B and C, C has more mass than B, right? It tilts down this way. The only question is, should I put C above A, at A, or below A? Because any part here are all above B. That's why we need the last diagram here. Now it tilts down this way. This means that comparing C and A, C has a greater mass. If C has a greater mass, therefore C will be above A. The mass of C is above the mass of A, which is above the mass of B. This has the greatest mass. This has the least mass. So greatest mass would be C only. Next question. There are two syringes, P and Q, each containing substances X. P contains substance X and Q contains substance Y respectively. Now, one of each syringe is sealed. So they're both sealed. That means that when this plunger is pushed, the substance inside cannot escape. The plunger in syringe P, that is this one, could not, very important, you should highlight this or underline, could not be pushed in. If it cannot be pushed in, it means that it cannot be compressed. Whatever is inside here cannot be compressed. That means that the substance inside here can either be a solid or is a liquid, because both solids and liquids cannot be compressed. So we'll take a look at these options. Gas definitely is out. Both gases are out. I'm left with either oil or water, because both of these are liquids. Next, the plunger in syringe Q could be pushed in slightly. Could be pushed in. Syringe Q is here. That means that the substance inside here, when you push in the plunger, this part is called the plunger. This substance can, this part actually moves, moves over somewhere, probably here. They say can be pushed in slightly, can be pushed in. That means that this substance Y can be compressed. If it can be compressed, that means that it must be a gas. Let's take a look now. We are left with only option 2 and option 4. This is air. Air is a mixture of gases, therefore air can be compressed. Oil is a liquid. Liquid cannot be compressed. So the answer for this is 2. Next one. Look at the diagram below. In this diagram below here, there's a flow diagram. We start off with some questions. Does it occupy space? Yes. Does it have mass? Yes. These two questions are important questions to tell us whatever is below here must be matter. This question tells us if something is a matter or not. So please pause the video here for a while to take down the annotations. Next, so does it have mass? Yes. Does it have a definite volume? Well, here is a yes and no. Now, before doing this, I'd like you to draw a simple table at the side and just practice this. Solid, liquid, and gases. Alright, the letters will represent the 3 states. So we're going to ask 3 simple questions. You would have done this in your workbook before. So here we're going to ask a few questions about, start off with volume. Does it have a fixed volume? Fixed volume is another way of saying definite volume. Does it have a fixed shape? And can it be compressed? And each of these will end up with a question mark because we're not sure, right? So let's pause the video for a while to try this, and then we will compare answers. Now, have you done it already? Let's take a look. Solid. Does a solid have a fixed volume? Yes, it does. How about a solid? Does it have a fixed shape? Yes, it does. Can solid be compressed? Of course not. Liquids. Does it have a fixed volume? Of course it does. Does it have a fixed shape? No, it doesn't. It depends on the shape of the containers you pour the water or the liquid into. And can it be compressed? Of course not. Finally, gases. Do gases have a fixed volume? No, because you can compress gases, therefore the volume will change. Does it have a fixed shape? No, because if you can compress it, you can change the shape. Now, having revised this, let's take a look here. Does it have a definite volume? Is answering this one, right? It says no. If it's no, then this must be a gas. So let's take a look at Z. When doing MCQ, we must always try to eliminate the options so our work is easier. So if Z is a gas, let's check. Gas. So that means that this must be wrong, this must be wrong. If these two options are wrong, that leaves option 2 and 3. Alright, now we have narrowed down to these two. Let's check maybe why. Yes, so it has a definite volume. That means that it must be either a solid or a liquid. Now, let's take a look at the next one. Does it have a definite shape? We know that a solid has a definite shape. If answer is yes, then X must be a solid. Does it have a definite shape? If it says no, no definite shape, that means that Y must be a liquid. Now let's take a look. Y is a liquid, is this one. X is a solid. Y is a liquid, that should be this. X is a solid, that will be this. X is a solid. Alright, X is a solid and Y is a liquid. So the answer for this is 3. Now this question. Now Osman pumps air into his bicycle tire until it is fully inflated. The tire can hold 200 cubic centimeters of air when fully inflated. He then continued to pump another 50 cubic centimeters of air into the fully inflated tire. Which one of the following is most likely to be the volume of air in the tire? So now a common mistake would be this. Now if you have not tried this, try this now. The common mistake is this. The tire originally can hold 200 cubic centimeters of air. And then you're going to pump in another 50 cubic centimeters of air. So many of the students who make the mistakes will be thinking, oh, I just need to add in and I get 250, and you will choose option 4. But this is wrong. Not because the math is wrong, but the science is wrong. Remember that this rubber tire is a solid, and a solid has a fixed volume. So in other words, even if you keep pumping air inside, the volume of this tire does not change. So how is it possible to pump in so much air inside the tire and the volume doesn't increase? It's because of a property of air, which is air can be compressed. If you understand this, then you know that you can pump in so much air inside the tire will remain the same in size, the volume is fixed because the volume doesn't increase. So even after you pump in 50 cubic centimeters of air, the volume remains the same at 200. Now, of course, what will change is the mass has increased. The mass of the air now has increased because there's more air inside the tire. But the volume remains unchanged. Get it? Because air can be compressed. Next one. Now let's try some open-ended question. John used a piece of plasticine and molded it into a bowl. Then he used the same piece of plasticine and molded it into a container. A plasticine is like a piece of blue tack. You mold it into different shapes. A cylinder is like this. This is the shape of a cylinder. Alright, a bowl looks like this. I have here a piece of blue tack which is similar to a plasticine. Now this is a solid. Alright, now some of you got confused with the idea of compress, thinking just because you can squeeze it and flatten it, therefore you're compressing it. Now in science here, it has a slightly different meaning. For example, if I were to now mold it into a bowl shape, alright, this is called molding, and now it is in a very ugly looking bowl-like shape. And then I use the same piece and now I mold it into a cylinder. The cylinder maybe looks a little bit more like this. Alright, I know it's not very pretty, but just bear with this. So it's something like a cylinder now. Okay. Now John's friend Bala made the following statement. The piece of plasticine can be compressed because John can press it. Is Bala's statement correct? Now, of course, the answer is no. Why no? Can he press it? Yes, he can. But has it been compressed? No, it has not. So there are two questions here, there are two question marks. Alright, first one is this is the second question. No. Why can't it be compressed? Because no matter how much I press it, it didn't become smaller. No matter how much John press it, the size remains the same, which means the volume remains the same. If the volume remains the same, it means the amount of space it takes up remains the same. Therefore, it takes up the same amount of space. It takes up the same amount of space. Why? Because it has a definite volume. Right? It didn't become smaller. It's not as if I squeeze it and then it became like this. Then you can say I've compressed it because the volume changed. But no, the volume didn't change. Now, state a property of the material that allows this to be molded. This material can be molded. Now, I cannot mold this, alright, into different shapes because this will have a different property than this. Why? You can say because this is stiff and rigid, whereas this one is flexible. So, it is flexible. That's why I can. Now, let me give you a bonus question. What if I were to tear this piece into three smaller pieces? 1, 2, and 3. Have I changed the volume of the plasticine? Did I change the total volume of the plasticine? And the answer is no, because I didn't change it. This one plus this one plus this one is equal to the same one as before. Okay? Now, next question. Jason carried out an experiment using 2 basins containing the same amount of water. He inverted a plastic cup and pushed it into the water in basin A. He made a small hole at the bottom of another plastic cup, which is this one, and pushed it into the water in basin B. Now, the water is not shown to you because you're asked to think about it and decide where will the water level be. In the diagram below, which is this one, draw the water level in basin B and in the cup when this cup is pushed into the basin B. Now, let's start the first one. There is some air inside here. There is some air inside this container. There's also air inside here. But this is a sealed up container with no hole. There's a hole here. What does it mean? If you were to push it in, the water level would be around this. The water level of the water inside the container is the same as the water level outside the container. Alright? This, and this are all the same. That would be your first answer. Explain what happened when Jason pushed a cup with a hole pierced at the bottom into the basin B. You've actually done this before inside your science workbook. The answer is quite simple. The air, alright, must be very careful. Where's the air? In the cup escaped from the hole in the cup. That's the first part of the answer. Because the air inside can escape after a hole is made, that's why the water could rush in and fill up the space left behind by the escaping air. So the second part is this. And the water in the basin can occupy the space left behind by the escaping air. Alright, that's how you explain this. Next question. Now, Amira wants to find out which is a faster way to pour out condensed milk from a tin. He makes 1 hole at the top of tin A and 2 holes at the top of tin B as shown in the diagram. Now, which tin will the condensed milk be poured faster? Now, naturally, most of you will write down the answer tin B, and you're correct. But the explanation is the problem. Now, when there are 2 holes, it means something. What does it mean? It means now that 1 hole allows air to come out. Imagine now I tilt this tin this way. Alright, and the bottom hole, this is the one, bottom one is here. The top one is this one. Alright, top one is the one in red. This is the top one. Now if this tin is now tilted this way, and the condensed milk inside now are going to draw in purple. Right, condensed milk now will be somewhere here, the level of the condensed milk inside. Now, how is the condensed milk able to escape from this hole? Well, if it escape from this hole, air could enter. Air could enter this. As air enters, this water can, the condensed milk can escape from this. So what it means here would be this. Air enters this part, tin B through the second hole, while the condensed milk escape or flow out through the first hole. Alright, this is the first hole and this one is the second hole. This is where air comes in, this is where the milk flows out from. This is how this works. And now to the last question. Sam wanted to pour some oil through a funnel, this is a funnel, into a flask as shown in diagram A. He noticed that the oil dripped slowly into the flask and stopped flowing after a while. Now how do you understand this? Is by examining the picture. Check, are there any gaps? No, this is completely sealed up. What is inside the flask? This part I'm pointing at. Oh, this part is actually air. Remember, air occupies the space in the flask. Now, can air be compressed? Yes, air can be compressed. That means that some of the oil can enter the flask. As it enters, it will compress the air. Push it aside, push it aside, push it aside. However, when air can no longer be compressed because there's so much of the oil has entered, so the oil will stop flowing. Why does it stop flowing after a while? Because air still occupies the remaining space in the flask. Simply because air in the flask occupy space, preventing more oil from entering it. Next one. Now notice now in this second diagram, this Sam improved his setup. He put a straw here, and this straw means that there's now a gap. The gap for air inside to escape. This idea is similar to having a hole for air to come in so the liquid can escape. In this case here, as the oil goes in, it will push out the air that is inside the flask. So the oil can take up the space left by the escaping air. So the straw allows the air in the flask to escape. That's the first part of your answer. Because you're asked to find out how to use a straw, no? How does the straw help the oil to flow into the flask? The oil is not flowing through the straw, but the straw allows the air in the flask to escape. This part is important. If you don't have this, it's kind of weird. The straw allows the air to escape. There's air here, there's air here, there's air here. Where is this air? Next part answer. So what if it allows it to escape? So what? So that the oil can flow in and take the space left behind by the escaping air. Right, that's how you explain this. The first part explains the purpose of function of the straw, 1 mark. The second part talks about the oil entering 1 mark. I hope you understand all this, and if you don't, just review the video once more. Have a great day. I'll see you again soon. Goodbye.